Hello and welcome to Lecture 18, Part 3 for Life in the Universe. This video, we're going to conclude Unit G. After taking a little bit more look at some regularities in the solar system, we're also going to look at some things about small solar system bodies. So for some of the general things, right here we have the top two images showing you the orbits of the major planets as seen from above. They all go around the sun in the same direction, as do all the dwarf planets and most of the small solar system bodies. The lower picture is an edge-on view of all 8 major planet orbits. And you notice they are all very close to being in the same plane. If you also look at the upper two pictures, the major planets' orbits are also all reasonably close to circles. None of them, even Mercury's, are really extremely eccentric. For the smaller things, the eccentricities can be higher, and they can have larger inclinations. Could be a bigger tilt relative to that plane, but they're mostly not out of really absurdly large. Mostly. A lot of regularity there. Turns out the sun and most of the planets also rotate in the same sense as that orbital motion. If you look at the satellites, all but one of the big satellites orbit their planet near the planet's equatorial plane and in the same sense as the planet's rotation. For the planets that have rings, it's all of the Jovian planets. Saturn's are the most spectacular, but all 4 Jovians have them. The rings are made up of a lot of individual particles that are each orbiting like a little bitty moon. They orbit the planet in the planet's equatorial plane and in the same sense as the planet's rotation. So there's an enormous amount of irregularity to the motions in the solar system. There are, however, some comets that orbit the sun in highly inclined orbits, and in fact, nearly in random directions, some even going around in the opposite direction as everything else. And some of these comets also have extremely high eccentricities. So in the next unit, when we look at how planetary systems form, we're going to need to explain all of this orbital regularity, as well as understand why there are some exceptions to it. Now, for the remainder of this video and the remainder of this unit, I want to tell you a little bit more about some of the smaller things in the solar system. So right here is a plot of the location of every known solar system orbit on June 5th, 2019, in the inner part of the solar system. So the yellow star symbol at the middle is the sun. And then we have the orbits and go from the middle up. Mercury, Venus, Earth, Mars, and the outermost one here is Jupiter. And let's see, where is Jupiter here? There. This X I just made is where Jupiter was at that particular moment. And then you've got all these other symbols indicating smaller things. So the red symbols are asteroids that have perihelion that brings it inside 1.3 AUs. You notice some of those are around the Earth's orbit, so some of them we could potentially hit. The green dots are asteroids, it's most of the things here, that have perihelion greater than 1.3 AUs. And then we have here and here, kind of ahead of and trailing Jupiter in its orbit around the sun, the Jupiter Trojans. And if you kind of notice here, you can make an equilateral triangle to the middle of those distributions, or you could, if you could draw better straight lines here with the sun, Jupiter, in the middle of those. Turns out those are a relatively stable place for something small to orbit. And we call them Trojans because of the tradition of naming them after characters in the semi-mythical Trojan War. Trojans on one side, Greeks on the other, although there's at least one Greek on the Trojan side and vice versa, indicating they must be spies. And then the blue squares, like this one right here, are comets that happen to be moving through the inner solar system at this particular time. Now, it's not nearly as crowded as it looks here, because at this scale, Even a single pixel green dot like that one right there is going to be much larger than what the size of that object, real object, would be if you shrunk it down to this scale. So even though it looks like you could walk most of the way from Mercury to Jupiter, just kind of jumping from asteroid to asteroid, you can't really do that. It's nothing like that scene in The Empire Strikes Back. The second Star Wars movie is always the way I will think about it, not as episode 5. The scene when the Millennium Falcon is being chased by the Imperial ships through the asteroid field. Maybe somewhere in the universe, asteroids are that densely packed, but not in the solar system. Um, Incidentally, if any of you are familiar with the Family Guy take on Star Wars, there is a great little thing from that scene where, following the real movie, C3PO and the Family Guy version played by Quagmire, I think, says, the odds of safely navigating the asteroid field are so many thousand to one. And Han Solo, played by Peter Griffin, says, what, we've got 3, 4 main characters on this ship. We'll be fine, which is an indication that Star Wars is neither Game of Thrones or Walking Dead. All right. Here are some face-on and edge-on views of some main belt asteroid orbits. I guess I should say a little bit about the nomenclature of minor planets. The International Astronomical Union is the organization that sets out nomenclature rules in astronomy. And for minor planets, especially in the main asteroid belt, things are basically more free than anywhere else. So they are given, when first discovered, they're given a provisional designation based on the year and half month in which they're discovered. And then once it's observed well enough to get a good orbit, it's given a running number. And then after that, it can eventually get a proper name. And with almost 1 million of them known, we'll probably never give them all of them proper names. The rules for the proper names are that it has to be pronounceable. There's a limit to how long it is, a limit of so many characters. Can't be too similar to one that already has been given. And not always been a rule, but political or military figures have to have been dead for either 50 or 100 years. Otherwise, we'd run into a problem that a North Korean astronomer would want to name one after Kim Jong-un, which the rest of the world wouldn't like. So basically give time for that to any bad reputations to get past. Anyway, the formal way to refer to one after it's been named is first the running number, followed by the name. So 1 Ceres, the first one discovered, is designated that. Full disclosure, 4587 Reese is not named after me. It is named after Martin Rees, who is the Astronomer Royal of Great Britain, also has the title Lord Rees of Ludlow. Pretty sure that's not our Ludlow that's in this general area. Probably the Ludlow our Ludlow is named for. Anyway, I've met him a couple of times back when he was only Sir Martin, and he's a really nice guy. When I told him it was an honor to meet the more famous Rees in astronomy, he told me that if my career went right, I could change that. And I still have a lot of work to do on those lines. All right. Here's a snapshot of every known object in the outer solar system on that same date. So now the innermost orbit, which is here, is Jupiter, and then Saturn, Uranus, and Neptune. Pluto is that symbol right there. Do you want to know where Pluto was at that time? And so anyway, you can see the centaurs are the orange and cyan triangles orbiting in this region. Comets, still blue squares. Then the various other symbols are either of subpopulations of Kuiper belt objects, of trans-Neptunian objects, either the Kuiper belt or the scattered disk. There's Gerard Kuiper, who proposed the Kuiper belt back in the 50s when Pluto was the only thing out there that was known. Anyway, you'll notice there aren't as many plotted here, but there probably are a lot more things in the population of trans-Neptunian objects than there are in the main asteroid belts. But these are much harder to find because they are further from us, which makes them fainter and makes them move slower relative to the stars, and they're further from the sun that makes them fainter. So after Pluto, which was discovered in 1930 by kind of a lucky accident, the next one was found in 1992. All right, let's see. Here are some trans-Neptunian object orbits, including that of Pluto. And so you can see the idea is they can be a bit more eccentric and a bit more inclined than that of the those orbits of the major planets, but they're not really um, extreme. And then we come to the concept with the of the Oort cloud. And the idea actually seems to have been originally due to Ernst Opik, but he only published it in Lithuanian or Latvian or some such Eastern European language. So his proposal wasn't very well known until Jan Oort independently had the idea almost 20 years later. So that's why Oort gets the credit for it. But anyway, they're both thinking about the comets that we see coming into the inner solar system, and you can only see them when they're close to the sun, on very, very eccentric, essentially randomly oriented orbits. And some of them, we calculate where aphelion would be, it's tens of thousands of AUs out. And so they hypothesize that these are representing a more or less spherically distributed population, very elongated orbits that we can only see when they're in the inner solar system. And basically, they're the outermost members of the solar system. And they spend most of their time out here. Kepler's second law says you move slowest at aphelion. So they might have an orbit of up to a couple million years. And most of that time is spent out here. And we only see them briefly when they come into the inner solar system. And based on the number that we see, there could be as many as 1 trillion of them. And here are a couple of Oort cloud comet orbits. The other two orbits shown in both cases are Neptune and Pluto. I know Jeff Larson, the guy who discovered this one. Nobody living knows the one who discovered the other one because it would have had its perihelion passage in 146 BC. And now it's over 900 AUs from the sun. I haven't updated this in 13 years. It's a bit further than it shows here, but it's still on its way out. And if it may be up to a couple million years before it comes back, so I wouldn't wait on it. All right, so again, a reminder for the attendants, you need to go take the attendance quiz on Plato. But for fun, I'm still including a secret code, and a question about the code will be in the quiz, but there'll be more questions actually about the subject we did. And anyway, the speculative fiction writer Harlan Ellison, mainly famous as a short story writer, but I guess he died about a year and a half ago or thereabouts. Anyway, he had a house in Sherman Oaks, California, overlooking Los Angeles, that was built by a very eccentric architect. And he actually liked to refer to it as, well, he had two ways he referred to it. Sometimes he called it Ellison Wonderland, making play on his name in Alice in Wonderland. And the other was the Lost Aztec Temple of Mars, which I think is a good description of it. And so anyway, Harlan Ellison's house being the code here. But like I said, you need to go take the attendance quiz on Plato. Well, that's it for this video. I need to hurry up and process these things because the chair that I sit in that I normally do this, it's mine during the day. The cat likes to sleep in it. Right now, he's on the other side of my computer screen, trying to sleep on the footrest in between my legs. Excuse me, and I'll probably have to try and figure out how to get up without disturbing him. I can get up without lowering the footrest, and then he probably won't move to the other part of it. So let's thank him for being nice on letting me continue to use the chair tonight. But I'm kind of caught up for where I wanted to be. So shouldn't have to be doing this so late at other times. So anyway, I'll let you know when the lecture 19 videos are ready. And until then.